Hello. OK. All right. Up next, we have Tish, who's a senior engineer at CSIRO Space and Astronomy Division, which sounds like such a cool job. He's previously worked with agencies like NASA and JAXA. So if you give him a round of applause. He's going to be talking about, I should have said what he's going to be talking about. Talking about OpenDataCube. And I'll let you take it away. There you go.
Thank you. I'll start by acknowledging the land and the people where we stand. We stand in the Ghana people's land, and it has never been ceded. I work with satellite images, and satellite images here look down on the Earth from space and sort of give us a perspective. There are no boundaries, and everything looks the same. And we try to organize the data and try to deliver it to people so you can make sense of things over time. OpenDataCube is a Python library for accessing and processing satellite imagery. I will sort of use this library metaphor a little bit. We talk about libraries in software engineering a lot, but libraries existed before software. I'll just try to use that analogy a little bit in my talk. A little bit about me. I'm a bit of a space cadet. I sort of enjoy working with satellites. I've been doing that since 2004 or so, for pretty much all of my career. Currently, I work at CSIRO. I'm on the OpenDataCube project steering committee. It's a fairly small community. I'm trying to do presentations like this to bring more interest into it, get diverse stakeholders looking after the project. Previously, I used to work at Geoscience Australia, which is Australia's geospatial agency. These are some of my team I used to work with. They have won a few government awards. Currently, I work at CSIRO, which is semi-government. There are other participants in the OpenDataCube project across the world, which makes it a thriving multi-owner project. If you go to the ODC GitHub, you can see lots and lots of people who have contributed over time. And like in open source, you sort of get to work with different people across different organizations, but work on the same project, so sort of gives you a bit of continuity. So I work with the last two people in this list, Matt and Rob, at CSIRO. So what is OpenDataCube? I started it by saying it is a Python library. So for some, that answer is true. So it is a Python library. Most of the code in the OpenDataCube is Python code, even though there is lots of SQL in there. Previously, there was a talk about PySpark. And it was funny how PySpark is a wrapper around Scala. So for me, I mostly work at the infrastructure layer, which I will talk about later. To me, it looks like a bunch of blob storage, an indexing database of some sort, a Kubernetes cluster. For an organization which doesn't care about the nitty-gritties, or like CSIRO, which is full of scientists, it's an easy method for gaining access to large amounts of satellite imagery through a single interface, being able to process it at scale and get the scientific questions answered. It doesn't necessarily be used for satellite imagery. It fits pretty well with that sort of dense array-style data. But it can be used for processing other sort of matrices, large matrix data, atmospheric simulations, and so on. So a bit of history. Where did OpenDataCube come from? How did we get here? So I found out these things. I was introduced to OpenDataCube just by accident. I was working at a startup in Nairobi, and I turned up at a university, and some people from the Ordnance Survey in Britain were being demonstrated the East Africa Regional Datacube. And at that point, I was like, oh, what is this thing? And I found out it's run by an Australian organization. And I came back and worked at Geoscience Australia and figured out some of this history. So Geoscience Australia is a data custodian for a lot of the data over Australia. They have been collecting Landsat data, receiving and collecting Landsat data for the 40+ years. A lot of it is collected by ground stations operated by Geoscience Australia. It's stored at NCI, which is the National Compute Infrastructure, a supercomputer in Canberra. Recently, European Space Agency has started the Copernicus program, and the Australia Regional Data Hub has collected a lot of the Sentinel data, which is a series of satellites operated under the Copernicus program. So that means there is around 5 petabytes of data collected, and I'll just go through some maths later on, which is going to explode a lot more in the near future. So OpenDataCube started as a sort of a way to organize this data in the HPC, in the high-performance computing supercomputer environment. I looked through the GitHub, and I joined the project around 2018 or so, 2019. And I looked through the history. It was released initially in 2016. And then it went through a bit of refactoring, renaming things from being a project for an agency to being open sourced. It was renamed from Australian Geoscience DataCube to the OpenDataCube. Currently, it's in a 1.8 version, fairly stable. It's used by organizations around the world, doing a bit of restructuring around how the index is maintained. So I'll talk more about the importance of indexing and these things I'm going over. But in the future, it's going towards this sort of machine learning queryable raster data sets approach, where things are metadata is a bit more flexible. You can query it easily and try to find answers quicker rather than be stuck in details of the technology implementation. So talking about details of technology implementation, we are in a technology conference, and some of these details are important for performance reasons. I'm talking about large amounts of data processing, so you have to store it efficiently and then get it back, bits of it quickly. So this is one of the images I like around the library analogy. So this is in Mona in Hobart. It's a piece of art called the White Library. So a library doesn't necessarily make things faster if you don't have the right way to find the right piece of data, right book. If there are no indexes, the books are in, pages are blank. And ultimately, you have to have an interest in finding the right thing. So once you have that interest, you go backwards and you organize your data. You have everything labeled. There are no missing bits or corrupted data. There is a synopsis and everything, but actual content is there somewhere in a durable way. So ODC tries to add those layers of organization on top of all of this data we are collecting from space continually to make it easier to access the volumes. So the early days, the storage backend for the OpenDataCube used to be NetCDF, which is common for storing simulation data, is tried and tested in the ocean and atmosphere community. It has a convention attached to it, but it's a convention, so it's quite flexible. So each NetCDF can be slightly different. So it was not cloud native. It couldn't scale. It required a very high performance Lustre-like file system, which is available in HPC environments to operate. So around 2016, 17, a new format came around, which we were going through the DjangoCon HTTP requesting. So HTTP has this idea of doing offset range requests. So you can store the data in index in the head and then actual chunks of data. So you can make a HTTP get range request to get the bits you're interested in if you have parsed the first little bit and you know where your data is in a large chunk. You have looked at the title page and you know which page to jump to. So that became a name known as the Cloud Optimized GeoTIFF, which is what ODC currently uses as its storage backend for most deployments. So it started with USGS, which was the United States Geological Survey. They had opened up access to the Landsat dataset, which was my first days of working with NASA, working with globe visualizers for Landsat. But the delivery system was very naive. You had to download all of the data in a tar format. And there was an experiment done to see, can we download the little bit we want using this offset range request if you store all of the blown up tar as individual TIFF files with the right index in the beginning to say, look over here if you're looking for this latitude, longitude that is of interest. So slowly, a lot of the other space agencies have adopted this standard for storing and delivering their data. It's powered by all of the different public cloud or even similar blob storage providers supporting the HTTP-based file access protocol. And the underlying libraries are the usual CURL library, which lets you make these HTTP requests. These days, I'm working towards supporting in OpenDataCube the ZAR format. GeoZAR has just come into the standards body to be organized and put in the right format with the right headers and so on, so you can look up a 3D range. So I'll talk about that a bit later. But obviously, it requires more memory because you're adding extra dimensions. The OpenDataCube data model, which I will go into a bit later, essentially has a snapshot in time with n number of dimensions attached to that point in time. So for a hyperspectral data storage, which has lots of bands, you'll have X and Y for the latitude, longitude, or meters in northing and easting, and then a band as a spectral coordinate. Following the success of the COG format, the other similar cloud-optimized storage formats have come around, and they follow the same idea. So this one shows the approach used in cloud-optimized point cloud, which is used for storing LiDAR data, individual point measurements. You have a header, you have points, you have chunk tables, and you have other metadata attached to it to scale the points as required. For vector data, you have GeoParquet. So Parquet is common. If you have spatial attributes attached to that, you can have GeoParquet is for storing spatial columnar data. So essentially, all of this comes down to the idea that you can read bits of it at a time very quickly. Still, in a real environment, there are limits. I use the Amazon example here. You can concurrently read one particular thing 5,500 times at the same time from the S3 store. So you may need to, for additional heavier machine learning loads where you're reading a lot, you may need to add additional layers of caching on top of that. So that's about how things are stored and read quickly in bits of interest. The other part is which bits to look up. Obviously, I said that each COG file has its own header to say which bit is of interest in that particular file. But in a particular data collection, you may have millions of files. So you'll have to have another layer of indexing on top to look up which particular file is of interest for your band, space, time, point of interest in which you're trying to perform typically some analysis, collating the data to some actual measurement on the ground, or performing some variability analysis over time. So that's where we come to sort of the idea of metadata and indexes over the actual raw storage. So continuing the library analogy, the data is very critical. So usually the metadata is sort of less important. You can rederive the metadata as long as you have high durability over the data. So occasionally you may need to reprocess the whole of the data, look at the actual content, and rederive the metadata. And the metadata format standards evolve as the data themselves evolve. New satellites come online with different amounts of dimensionality about them. And their internal representation from the space agency of the metadata, because they're an independent entity, they're sitting at the source, they get to dictate how they do things. Slowly, those standards are emerging because people are interested in multi-sensor fusion. So your data is not useful in isolation, it's useful together with something else, and that they can only be brought together if they have a shared sort of data model to work together. So the current convention is the spatiotemporal asset catalog stack. OpenDataCube was built pre-stack, so it has its own slightly different convention, But the Open DataCube community worked a little bit, Alex Leith and others worked a little bit with Stack to bring some of those understandings, because the implementation existed before the standard. So this happens a lot of the time. To bring some of those ideas to say, this is actually practically usable. It would be good to have these things in the standard everyone else is choosing to adopt. Even these days, there are Stack implementations which are not compliant, but there are more maturities coming in place to make sure conformance testing is done in a Stack catalog implementation and so on. So being an Open DataCube, sort of injecting data into it, I do Kubernetes every day, so you sort of are an YAML engineer. You don't write code, you write declarative things to say things look like this. This is the spec of the actual file. This is the coordinate system you're in. YAML is nice because you can write sort of descriptions next to it. Then the data model comes there in creating these different objects in the YAML that you are attaching to the binary blobs that are the satellite imagery raster data sets to say, this is a product, this is from different collection of observations, this is a single observation at a point in time and place, and these are the components inside it, and then these are the actual measurements that took place. And then for human readability, we don't respond to 950 nanometers well. You say what color that is. But that sort of becomes a bit of a liability if you have lots of colors. If you have 400 different bands, it's like near red, almost red. It could be red, salmon. Anyway. So what does the metadata look like? And this is actually something like in any other convention-based thing, people find challenging in adopting Open DataCube. You have to get a handle on what the data model looks like and get the products that you have. Say you have some UAV data, and that doesn't have a predefined metadata set. You'll have to come up with one to put it into the Open DataCube. There are some helper scripts. We are trying to make that more mature to make it easier to put any metadata on top of the data sets you have. Or you can also define your own specification. If you think this model is insufficient, you want to have more descriptive things about your platform, you can add more into it. The flexibility comes at a cost, but yeah. So the initial implementation of Open DataCube uses PostgreSQL as a document database. So PostgreSQL is a relational database, but it has this idea of a JSON blob. So in first days when I was working with Open DataCube databases, I was migrating databases, and I found very large JSON blobs storing this metadata greater than 2 megabytes in size, and then it sort of comes with the flexibility in being able to define arbitrary metadata, comes with the downside of your data being very blobby in this particular backend implementation. So I'll talk about like future index implementations that we are looking at. So the core part of Open DataCubes is a bit of the core code. Has this schema where we are moving from PostgreSQL with JSON blobs where the geospatial data was in the JSON as strings to be more geospatial with implementation of PostGIS, which has geospatial functions built into it. And then you can have the data model quickly look up the spatial query of where the data set is looking for, you're looking for is found, and then there are also time ranges, and then any other metadata is stored as metadata, which is sort of doesn't play well with our SQL Alchemy guidelines, but is still there from the pre-PostGIS world. The other way for having a backend is sort of separating the database and layering an API, the Stack API, as I was saying. The Stack has a search API. So putting that on lets you just make a similar query request, not to a database as a SQL query, but to a web endpoint, and then you can find out what are the data sets available. I think I have a quick demo on that. Let's see. So you can use this library called ODC Stack. And you can say, OK, I want to look up this stack catalog and Sentinel-2 cogs over sometime in January. And it gives you a bunch of JSON. Don't have to worry about it. Lots of stuff available. And there are some scenes available over Adelaide, and then you can have them in the OpenDataCube data model to process. So sort of the YAML engineering becomes a bit of more traditional JSON engineering with REST APIs, and you can look up things and process them. So what is the big advantage, big idea behind this? What OpenDataCube is providing is being able to lazily operate on a lot of this data. So the way we were talking about in Spark or in the previous DAG talk, you actually set up the workflow you're trying to apply on this large collections of data. You can test it over small samples and then increase your query space to apply the same operation lazily over large things and spin up clusters to perform those operations. So the magical command it usually provides is this dcd.load using your parameterized query for your resolution, where you're looking for the data. And it returns the results in an X-array abstraction, where you have the different dimensions, and X-array is sort of a hybrid between pandas and NumPy. You can look up things by their dimension and work in arrays. And X-array is also compatible with Dask, which lets you create this lazy graphs. Then you can operate over and farm out the data across a large cluster that you spin up. The bigger part of it is around that 5,000 limit. You can have 5,000 CPUs concurrently loading from your storage and processing your data. The data model has some shortcomings. I did a lot of my work in my PhD on SAR. When you're trying to reproject data, because SAR pixels are in complex domain, OpenDataCube needs some enhancements, not there yet, to convert the complex data and restructure it better for your even grids or have uneven grids. You can have uneven grids in the coordinate system. It's not implemented yet. The other one is obviously the HyperSpectral one I was mentioning. Because of the way we make it easy with string aliases of different bands, you will probably try to name things a lot or just have to add another dimension where it's like a numbered account. Instead of having names, you just have numbers on the bands, and you have some sort of mapping elsewhere to say these are the ranges in which you have your bands. So this is like just a quick example of some maths of the modern hyperspectral satellites coming on. Just some quick back-of-the-envelope maths. You have 7.6 million square kilometers in Australia. You have 30 meters spectral, say. Creates 8.5 billion spectrals over Australia across the bands. And you have daily mosaic. So if you have like many years of data, it builds out to exabytes of data. And OpenDataCube doesn't have a good way of scaling out. You can store it. But it doesn't have a good way of scaling out to read that very quickly in parallel and process it yet. So talk about the scale of the processing that has been done and the Dask way. I think a survey was done. Roughly 10% of the Python community uses Dask. Just how many people use Dask? Yeah, a few people. Yeah, so maybe in this audience less than 10%, but yeah. So around 10% of overall Python community uses Dask. Dask is a structured way of doing multiprocessing over numerical data or even any other data. Thank you. So for the OpenDataCube usage, it basically embeds a duck array, a Dask array with embedded NumPy arrays, which are then passed around between the nodes or threads, depending on the sort of cluster you're setting up in order to scale out the processing. You can start up a local cluster, or you can start up a large 1,000 CPU cluster. It depends on what sort of resources you have available. And I work in Kubernetes land most of the time, and you set up a job, and you have runner pods spread across multiple nodes where the same Python code is sent out, parameterized with different sources that OpenDataCube has looked up of the data source, and then operations are applied by each pod independently based on the Dask graph you have set up through OpenDataCube to perform your processing. So this is like a sample scaled processing. I think bigger processings than this was done. So this was done as part of the Digital Earth Africa project, which shows starting up a 4,000 CPU cluster and consuming 50 terabytes of RAM to do whole of Africa processing. And these are some of the results you get using the Landsat data archive of, say, evolution of a city in Egypt. The OpenDataCube project also has sort of, other than the core functionality of being able to load and index lots and lots of satellite imagery, has a few web applications that are sort of offshoots to it. One of them is essentially being able to see the index, what data you have in your DataCube. You will be able to query how much of it is there. This is the DataCube Explorer application. This shows that in AWS, the Digital Earth Australia project has 500,000 data sets, or 400,000 data sets covering all of Australia for this particular collection of data. There is also an open web service, so it produces the tile services, WMS, WMTS, also actually fetching the data, which is the web coverage service. So this particular instance is the project I work on called AquaWatch, which stores data for aquatic reflectance. So obviously, that's a segue to the different OpenDataCubes as infrastructure running. You can have it locally as your own DataCube, but there are large-scaled deployments. Digital Earth Australia from Geoscience Australia is one of them. I worked on Digital Earth Africa. Currently, some people are trying to set up something for the Pacific. The work means me to take breaks. It's good that my time is coming to an end. I work on the CSIRO easy DataCubes, which one of them is the AquaWatch one. There are lots of them around the world from CSIRO. And sort of it looks, OpenDataCube is a core component, but there's lots of other stuff around it. And it's sort of, there are 1,000 moving parts in it, so I just put those there. The alternative index backends is something we are looking to enhance to scale down so that you have embedded databases, or scale up so that you can actually just have not a database, but just look at, query the blob stores directly and index them through some sort of data lake approach. And also adding HyperSpectral support to create these large task graphs across the band dimension efficiently and being able to index that properly. Happy to have any questions.
Thank you, Tish. That's great. We might be able to fit in one question quickly if anyone's got any, as long as it's a short answer. I can't see. Oh, just over here.
Thanks very much for your presentation. You mentioned that there were some issues using SAR satellite data. Did that mean that we cannot use like this tool for SAR satellite data, or is that it's slower and there are some limitations? And also, can you use this as well with private satellite data providers, or is it limited to Landsat and European Space Agency products?
So the there is limitations in using the single look complex data, which is not actual reflectance data, but is earlier in the SAR processing, where the pixels are not square and they are complex numbers. But if you have georeference data where you only see the reflectance, then that's fine. So there is actually a Sentinel-1 collection for all of Africa and so on available. Any data can be put into it. People build their own private data cubes based on, say, Planet or any other satellite imagery they have. But then they have to store it themselves and manage access to it and so on. So they have to set up the infrastructure to manage that private data themselves. A lot of people have used OpenDataCube in their own private instances to manage their data collections.
Thanks a lot.
Brilliant, thank you. The sheer amount of data involved in this kind of thing makes my head spin, to be honest. But thank you so much for that. And here's a token of our appreciation.
Thank you.
There you go. Thanks a lot. Thank you, Tish.